Here we've got the transformations exploration number 1. There's another one that's going to follow. This one's focusing on actual equations that you're familiar with and transforming them. So on the left we have an example of just graph this function f of x equals x minus 3 squared plus 2. Here we have that graphed. Another way of saying this is to say let f of x equal x squared and then graph this. You'll notice that this isn't squared now, this is using f referring to this parent graph x squared. So this really means to graph the same thing. We're saying it in two different ways here. It's a shift to the right 3 and up 2. You can see the vertex is at 3, 2. Same idea over here. Here we've got the square root function. I could just give you this to start with, or I could define what g of x is here and then say graph g of x plus 2 minus 5. It still means a shift left 2 and down 5. If this is the origin, left 2, down 5, that's where that little locator point is for the square root graph. Alright, so what we have then is we want to make sure you understand shifts. And this should be a review from a previous year in algebra. This is a pre-calc class, so it should be a review from a previous year. If I've got an original function, h of x plus 2 plus 6, that means that the graph's going to move left 2 and up 6 units. So you'll notice the x plus 2 is in parentheses, and the move that it does, the shift, takes every point and moves left 2 units. So the 2 comes from there. The fact that it's going left is because it's plus. And then this plus 6 means it goes up 6. So over here we've got f of x plus 5 minus 3. So that would mean this graph would shift left 5, down 3. And also it's important to keep in mind, we don't know what the original graph looks like. I don't know what h of x is, or f of x, or g of x. And it doesn't really matter. We know that this transformation represents a shift right 7, up 2. Left 4, down 7. So as we keep going down this exploration, here's an example. Here's what the parent graph could be. Here's the transformation. This is what the expression would be. And then this means shift it right 3 and up 2. And it doesn't matter if I'm talking about x squared or the square root of x or any of these. As you fill them in, you'll get these new expressions that'll use the parent graph. So I've got an answer key. I'll show you what that looks like. For example, the square root of x. So instead of x, we put x plus 2. And then outside of the square root, we have plus 5. This still means a shift of left 2 and up 5. For the reciprocal function, 1 over x, instead of x, x minus 4 is replaced and a plus 3 on the outside. Make sure you're writing those correctly. The very last one that I have on this document, you got to choose. I said simply shift left 2 and up 30. So you would have to have some sort of a shift left 2 and up 30. And I just decided to use the reciprocal function. We're going to go to the guess the glue in on the back. Alright, so here's your solution. Here's the real glue in. You can check it against your guesses. Here's the graph of x squared. It was f of x equals x squared. Here's the graph of f of x minus 4 minus 7. Now I know this is squared because it's referring to f, and f was a quadratic. It's x squared. That's the parent graph. So I just shifted it to the right 4 and down 7. There's my new vertex, and graph it using the same pattern when the a value out front is 1. It's just over 1, up 1, over 1, up 3, over 1, up 5. That's for a parabola. Here we've got the square root. Here's the original one. It's a sideways parabola, except half of it. And then this was shifted left 2 and up 4. Same idea, just shifted. So these two questions down here, we're looking ahead. What would the transformation 2 times f of x minus 3 plus 3 do to the original graph? Well, these would shift it. The 2 would cause a vertical stretch because it's a 2 on the outside. Here we've got another vertical stretch. It's actually going to cause a reflection too. A negative sign being multiplied times g of x in this case would cause it to be a reflection. The stretch would come from the 3 and then it would shift down 7. Turns out there's an order that you have to do all of these transformations, and that's what I'm going to do next. Alright, so in the last transformations exploration, we did transformations with an actual graph, a function that you're used to, square root of x, x squared, x cubed, things like that. Well, now what we're going to do is we're going to take a different looking graph, with some points labeled, and we're going to transform it. So on the left we've got the graph of f of x, defined here, and I want to use that as my parent graph to then use this transformation to graph the new one. So each number and operation that's going on here means to do a specific thing to each coordinate. And a great strategy for starting off is to label where your current points are. So for A, I'm going to figure out where A is. It looks like it's at -6, 3. B is at -2, -3. And C is at 3, -3. This is a great way to start off. All right. So now I want to figure out what's going to happen to each one of these coordinates as I go through this transformation. So let's start off with the 2 out front. This 2 out front means multiply the y coordinate by 2. So you're going to do the stretches and then the shifts. The shifts are these -4 or +4, anything that's in here that's adding or subtraction, or out here, adding or subtracting. So we're multiplying y by 2 because there's a 2 outside of the f of x. Remember, f of x was just y. It's another way of saying y. So if I have like 2 times f of x, you're taking all the y coordinates and you're multiplying them times 2. The next thing you're going to do after that, then you're going to move the point right 4. And then you're going to move the point up 2. Now you can move up 2 and then right 4. I just did it in the order that I saw it. So you got to multiply the y coordinate by 2, then move right 4, and then move up 2. So we're going to do that with each point. And the way that I do it is I start off with my original coordinate, my pencil point on that spot. So -6, 3 would be right here. And now I need to follow all these steps. So multiply y by 2. Well, that means that my y coordinate would change to +6. 3 times this 2 would give me +6. So now I'm at -6, +6. Then I can move right 4. So notice I'm just keeping my pencil point in that spot, changing it, not putting a dot there, and then following the last shifts. Move right 4, 1, 2, 3, 4, and up 2. 1, 2. That's my new point. I'm going to label that one A, and then there's this little prime that goes above it, a little dash. You might remember that from geometry. Do the same thing with all 3 points. -2, -3. So -2, -3. Okay, so now I need to multiply y by 2, which gives me -2, -6. Then move right 4, 1, 2, 3, 4, and up 2. That's where point B is. Sorry, B prime. C, here was 3, -3. Multiply y by y by 2, and you get -6. Then move right 4, 1, 2, 3, 4, and up 2. 1, 2. That is C prime. Last thing you need to do is just connect the dots in the order that they were connected before. So from A to B, from B to C, and there's your transformed graph from the original. You can kind of see how it's stretched vertically, not so much horizontally, although sometimes it's hard to tell if it's a vertical stretch or a horizontal stretch, just visually. For this next one, it's going to be very similar, so try it on your own and see if you can get it. And then there's one more tricky one down here that I'll reveal the answer in a sec. Alright, so right now my focus is on this graph. I labeled all the original coordinates, and then here's what you would have needed to do. Multiply y, now it's by a -2, and then you're going to move right 3 because of this one, and down 3 because of this one. So here's all my original coordinates, and then this is what I would have gotten. So I would have put my pencil point at -5, -2. I would have multiplied y by -2, giving me +4. I would have moved right 3, 1, 2, 3, and down 3, 1, 2, 3. That's how I would get to A prime. And I do the same for A, B, C, and D. Label them, connect them in the same way. You might see that this is actually a reflection over the x-axis because I multiplied times a negative. On the one below that, something different happens. Our shifts when we are in parentheses are always counterintuitive. So this says x -3, we got move right 3, and most people picked up on that. It turns out when we do the multiplication inside as well, so this would seemingly be multiply x by 2, but it actually means divide x by 2. it's you could just say multiply by 1/2. It's the reciprocal, right? So if this was a 1/2 here, it would actually be multiply times 2. So because there's a 2 right there, it means divide x by 2. So here's my coordinate, -8, 3. Divide x by 2. So I take that -8, I divide by 2, I get to -4. I then can move right 3, 1, 2, 3, and up 4, 1, 2, 3, 4. That's how I got to a prime. The very last one, I wrote down exactly what you need to do. Multiply x by -2. Again, it's the reciprocal of this. So the opposite of 1/2 would just be multiplying by 2. And there's the negative sign, so keep that with it. The shifts happen afterwards. So always do the stretches, which is the multiplication, and then do these shifts left to right. All right, for the very last bit of this transformations piece, we've got the real glue in. So here's an example problem. We've got a point 3, -4 that's on a graph, and we're trying to figure out what point is on the graph of this. This is a transformation of the original function f of x. We don't know what f of x is, and we don't need to try to figure it out. We just need to figure out what other point would be on this graph, knowing that 3, -4 is on the original. So what happens is all of these little pieces that I highlighted here do something to the coordinate. And you want to make sure you apply those things in order. So we have to do the stretches before we do the shifts. The stretches are when we're doing the multiplication times 3, or inside parentheses, we have a multiply times 1/4. Those are the stretches. The +2 here and the -5 there, that is the shifts. So we're going to go through. We got multiply y by 3. That's the first thing. Now I could have easily done multiply x by 4, but both of those come from here and here. I color coordinated it. So 3, -4, you multiply the y coordinate, -4, by 3, because there's this 3 outside. All right? So it became 3, -12. I then took the x coordinate and I multiplied times 4. That 1/4 dictated that. Kind of looks like you should multiply x by 1/4, but it's actually the opposite of that. So you could think of it as dividing by 1/4. I just think of it as multiplying x by 4. So that's how I got 12, -12. Then I can do the shifts. So 12, -12, I subtract 2 from x. I get 10, -12. Take that coordinate, subtract 5 from y, I get 10, -17. It's a very numerical way of doing this transformation. And then I just write a summary statement. 3, -4 becomes 10, -17 after the transformation. Some other little notes. Here's an example problem down here with the graphs. And then just some things that you need to keep in mind to clear up some confusion. Negative f of x and what that means to do with the coordinate. F of -x, what that means to do with the coordinate. 6 times f of x would be multiply y by 6, whereas f of 6x means to divide x by 6. Here's f of 1/3 x. That means take the x coordinate, multiply times 3. So you can see how the operations reverse when we're in parentheses. What doesn't reverse, this -x doesn't mean multiply x by 1. I don't mean opposite sign, I mean opposite operation. So if you see multiplication in parentheses, it means division, right? In the same way that our shifts, a +2, x +2 in parentheses, means move left 2. It's a little bit counterintuitive. I hope that helps.